Good day, I'm Norman Wobberger. Today we're going to have a further look at interval arithmetic, which arises naturally when we're doing scientific measurements. So the idea is that instead of doing arithmetic with single numbers, we can also think about doing arithmetic with an interval. Maybe the interval 2, 5 or the interval 4, 8 and so on. And it turns out that there are significant differences depending on whether we're thinking about intervals of natural numbers or intervals of integers. And intervals of rational numbers, which we'll also introduce later on, is very similar to intervals of integers. I'm also going to change my notation a little bit. This is a suggestion of a viewer, Peter High 503, I thank him. It's a good idea, I think, to rethink notation every so often and ask ourselves, are the terms that we're using really the right ones, the best ones for our practice? So he suggested that instead of talking about a natural number interval with this name, num interval, which I talked about last time, that we rather use interval nat, where nat is short for natural numbers. Now I've been thinking about making this change myself actually for a while, because when we started off introducing numbers, the first numbers that we considered were the natural numbers, and we just called them num, N-U-M for short. But later on, when we introduced other number systems, it was clear that num was just one of many possible number systems, perhaps the primary one, but nevertheless still one of many. And so it makes sense to give it some more descriptive name. So nat is something that we're going to be now using instead of num. Okay, so nat means the type of natural number. 1, 2, 3, 4, 5. And I'll just put the type of number that we're talking about after the interval. So we're talking about an interval of natural numbers or an interval of integers. This also more or less parallels with what we were doing with polynumbers. We had polynum before, and now we can talk about polynat or polyint. Alright, so let me remind you of the basic idea. So an interval nat, or an interval over the natural numbers, is by definition an expression like this. An expression involving two natural numbers, m and n, and with a requirement that the first one, m, is less than or equal to the second one, n. And we had a definition of addition of such intervals. Here is the definition. We just basically add the two elements in the first position, and we also add the two elements in the second position. And multiplication is exactly the same. So these definitions are not arbitrary, but they rather correspond to a very natural scientific process. So the justification for these definitions is as follows. Suppose, for example, that we have 2, 5 and 4, 8, and we're interested in the sum 2, 5 plus 4, 8. Arithmetically, this is going to be 6, 13. What does it mean geometrically or scientifically? Well, 2, 5 represents a range of values. It represents any one of the natural numbers which are contained in this segment from 2 to 5 inclusive. So we can think about this interval in our minds as representing any one of these four natural numbers. And 4, 8 represents any one of these numbers, 4, 5, 6, 7, 8. And when we're adding this interval with this interval, in our minds what we can think about is we're taking a random element in this first interval and another random element in this second interval, and we're adding them. And we're seeing what are the possible range of values of that arbitrary sum. For example, if we added 2 and 4, well, then we would get 6. If we took 3 and 7, we would get 10. If we took 5 and 8, we would get 13. Altogether, the range of values that we get stretches from 6, which is the minimum, occurring when you take 2 plus 4, all the way up to 13, which is the other extreme when you take the largest one in this interval, 5, and the largest one in this interval 8, and add them. So that's the meaning of addition, at least. It corresponds to a certain amount of uncertainty in addition. So we're adding some number which belongs to this interval to some number which belongs to this interval and asking what are the range of possible sums that we can obtain. And the story is very similar for multiplication. When we multiply the interval 1, 3, for example, by the interval 2, 5, arithmetically we get 1 times 2, 3 times 5. And what that corresponds to geometrically or scientifically is we're allowing ourselves to choose any number in this first interval 1, 3. So either 1, 2, or 3. And we're allowing ourselves to choose any number in this interval 2, 5. So 2, 3, 4, or 5. And then you can multiply those two numbers together. The range of possible values goes from, the smallest would be 1 times 2. The largest would be 3 times 5. So you can go all the way from 2 up to 15. It's important to observe that not all values are possible. We, for example, cannot obtain 11 as a product of something in here times something in here. So we don't need to be able to get every number in this final interval. We just need to be able to say what the range of possible values is. We're saying that any number that we get by taking a number in here and a number in here and multiplying them will necessarily be in there. And this is sort of the smallest interval that has that property. Okay, so here's a generalization of what I just said. It's a little theorem that if we have two intervals with natural number entries and m belongs to I, or in other words m has property I, and I remind you this is our notation for thinking about the interval as a property of natural numbers. So m has property I means exactly that m is between the bounds of I. It's greater than or equal to the leftmost entry of I and less than or equal to the rightmost entry. So if we have m belonging to I and n belonging to j, then m plus n belongs to I plus j. And m times n belongs to I times j. We could, in addition, say a little bit more. We could also say that I plus j is actually the smallest interval that has that property, and I times j is the smallest interval that has this property. So let's have a look at a few examples of how we might use this interval arithmetic. Suppose that Tom has between 10 and 12 apples. And when I say that, I mean he could have 10, he could have 11, or he could have 12. So between means including 10 and 12. And that he also has between 25 and 30 oranges. Then how many pieces of fruit does he have altogether? Well, the interval 10, 12 represents the quantity of apples that he has. The interval 25, 30 represents the number of oranges he has. If we add these two intervals using interval arithmetic, we get 10 plus 25 is 35, 12 plus 30 is 42. And so the total number of fruit that he has is somewhere between 35 and 42. That's sort of the minimum possible, and that's the maximum possible. Here's another example. Sue has between 6 and 8 coins in her pocket. And the coins are either nickels worth 5 cents, dimes worth 10 cents, or quarters worth 25 cents. We'd like to know how much money does she have in her pocket? Well, we can't say for sure because there's uncertainty. There's uncertainty in two different ways. We're not sure how many coins she actually has, and we're not sure which coins she actually has. Nevertheless, the range of coins that she has is represented by the interval 6, 8. And the range of values of the coins is represented by the interval 5, 25. And if we multiply these two, we get the minimum would be 30, the maximum would be 8 times 25, which is 200. This is telling us that she has between 30 cents and $2 in her pocket. So the minimum would be that she has the minimum number of coins of the minimum value, so 6 times 5. And the maximum would be the maximum number of coins times the maximum number of values, which would be 200 or $2. Here's another example that might come up in a sort of scientific situation. We have a very simple electric circuit, and Ohm's law tells us that if we have a voltage V here, represented by some kind of battery perhaps, we have a current I going through our wire, and we have some resistance, maybe a little lamp that's being lit up there, value R, then the voltage is the current times the resistance. So this is a fundamental law in electricity. So suppose that in this particular situation, the I is measured by someone, and we find that it's more or less 2. But more specifically, we know that it's 2 within a certain range. So it's 2 plus or minus 0.1. And current is usually expressed in amps. So this would be 2 amps with a little bit of error, 0.1 possible error in either direction. And suppose we also know that the resistance, which is usually measured in ohms, happens to be 7. Resistance of this lamp is 7, but there's also a little bit of error, perhaps plus or minus 0.5. And we'd like to know, so okay, what is the voltage? Well, the naive thing to do is to say, well, it's I times R. I is more or less 2. R is more or less 7. So I times R is 2 times 7, or 14. The voltage is 14. And that's roughly correct, but it doesn't take into consideration the errors that we have in both of these quantities. So a more refined analysis might use interval arithmetic. This current here is actually represented by this interval, 1.9 to 2.1. The resistance is measured or represented by this interval, 6.5 to 7.5. If we multiply them, because we're multiplying current times resistance, then the lowest value is 1.9 times 6.5, which is 12.35. And the top value here is 2.1 times 7.5, which is 15.75. So in fact, the range of possible voltages goes from the minimum of 12.35 up to a maximum of 15.75. And if we wanted to express this in a way that's sort of similar to this, what we could do is we could take the average of these two values, so exactly the halfway point, which we get by adding them up and then dividing by 2, and that turns out to be 14.05. And then the difference between that midpoint and either this endpoint or that endpoint is 1.7. So another way of saying it is that the voltage is 14.05, that's sort of the central value, plus or minus 1.7 possible in either direction. Now, just as a bit of an aside, this 1.7, sort of the amount of error that's involved in the voltage, you might ask, well, how does that come about from the error in the current, which was 0.1, and the error in the resistance, which was 0.5? And the kind of a clue there is to note that if you take 7 times 0.1, you get 0.7, and if you take 0.5 times 2, you get 1. So this error here can sort of be thought of as 7 times this error and 2 times this error. So the errors are kind of combining to give you the error in the product. All right, so I think this makes it very clear that sort of an interval arithmetic point of view can help in clarifying what goes on in a scientific experiment or measurement. And it also illustrates that even though we may have a situation with some uncertainty, we can deal with that uncertainty in a more precise way by talking about intervals. So let's talk about the laws of arithmetic for intervals with natural numbers. There are the commutative laws. that I plus j equals j plus I, and that I times j equals j times I. I and j are two natural number intervals. There's associative laws, that I plus j plus k is the same as I plus j plus k. And similarly for multiplication, that I times j times k equals I times j times k. And a distributive law, that I times j plus k equals I times j plus I times k. Now these laws all follow from the corresponding laws in the natural numbers. I remind you, the natural numbers used to be referred to as this type, and now we'll probably more use NAT for the natural numbers. And the reason is because the multiplication and the addition of intervals is done component-wise. The leftmost entries are being added or multiplied exactly as usual, and the rightmost entries are being added or multiplied just as usual. So if you think about it, the standard laws here apply to the leftmost entry in the sum or the product, and they apply to the rightmost entry in the sum or the product sort of separately. And so it's straightforward that these laws are going to be working. For example, the distributive law. Here's just an example. We're multiplying 1, 3 times the sum of 2, 5 plus 4, 6. 2, 5 plus 4, 6 is 6, 11. When we multiply that by 1, 3, we get 6, 33. On the other hand, 1, 3 times 2, 5, and 1, 3 times 4, 6 will give us, this product is 2, 15. This product is 4, 18. When we add them, we get 6, 33. And I'll point out that the element 1, 1 is playing the role of the number 1, because 1, 1 times any interval mn is mn. And I also point out that if we extend our numbers just a little bit by adding 0 as well, then we can also talk about this element, 0, 0, that interval, and that has the property that when we add it to any interval, we get the other interval. So the laws of arithmetic for natural number intervals are very simple. They're really just exactly the same as the laws of arithmetic for natural numbers. However, for intervals using integers, the story is a little bit different. So now let's talk about interval arithmetic for integer intervals. Intervals whose endpoints are integers, so including negative numbers. The addition of such intervals is the simplest operation, and it's the same as for natural number intervals. We just add component-wise. And the reason is, I think, geometrically pretty easy to understand. Suppose, for example, we have the interval minus 3, 2, and we're adding the interval 4, 7. So there's minus 3, 2, which we can represent geometrically as the range of values from minus 3 up to 2. So 1, 2, 3, 4, 5, 6, any one of those 6 values. 4, 7 represents this range, 4, 5, 6, or 7. Now if you take a number in this range and another number in this range and you add them, then what are the range of possibilities? Well, the smallest value you can get is by taking the smallest number here and the smallest number here, minus 3 plus 4. So the smallest number you could get would be 1. The biggest value you could get would be to take the biggest number here and the biggest number there and add them. You would get 9. So that's why we define the addition this way, because it reflects this idea of taking a random or an unknown number in the first interval, an unknown number in the second interval, and adding those two unknown numbers. Subtraction was a little bit more unobvious. AB minus CD is A minus D, B minus C. Let's understand the reason for this definition by looking at a picture. So here's an example, minus 1, 3, minus the interval minus 2, 4. So where are they? Here's our line, and minus 1, 3, that's this interval right here, from minus 1 up to 3. So any one of these values here, minus 1, 0, 1, 2, or 3. And minus 2, 4, that's going from minus 2 up to 4. That's in green here. Any one of those values. So what we're doing is we're taking a first number somewhere in this range, and then we're taking a second number somewhere in this range, and we're taking the first number minus the second number. And asking, what are the possible range of values that we can get? Well, what's the smallest possible value we can get? The smallest possible value we can get is if we start with the smallest value in the first interval, and we end up subtracting the largest possible value in the second interval. So if we take minus 1 and we subtract 4, then we go all the way down to minus 5. That's the smallest number we can get. So that's this number minus this number, or A minus D. And what is the biggest number we could get? So we're taking one of these numbers and subtracting one of these numbers. The biggest number we can get is by taking the largest one of these numbers, which is 3, and subtracting the smallest one of these numbers, which is minus 2. So 3 minus minus 2 actually gets us up to 5. So this minus this value is the largest possible value. So that's the B minus C term that's appearing there. So this is the justification for this definition. This definition is not arbitrary. It reflects what actually happens when you have two intervals and you take a number from one interval and subtract another number from the second interval and ask, what are the range of possibilities for that difference? So last time I gave you an exercise to try to figure out what the definition of multiplication of two such integer intervals might be. And it's a little bit more challenging to come up with that. In fact, it's not easy to give a concrete formula in terms of one of these times the other, comma, one of these times the other. We actually have to have a much more flexible attitude. What we need to do is we need to take all possible products of these two elements with these two elements. So A times C, A times D, B times C, and B times D. We have to take those four products and we have to look at those four numbers. And we have to choose the minimum of those four numbers. That's the left endpoint. And we have to choose the maximum of those four numbers, and that's the right endpoint. And that's probably the simplest way of saying how you define the product of two integer intervals. So it's a little bit more subtle. And why do we need to do this? Well, I'm going to give you some examples here to illustrate that various possibilities can occur. All right? And in fact, when you were doing this exercise, probably this is the first thing you should have done. You should have said, well, let's have a look at some examples and see what happens in a variety of examples to get the hang of it. It's just generally the best way of trying to understand a pattern that we're not that familiar with. Work through some examples, list them, organize them in a nice way, and have a look at what's going on. So for example, minus 1, 2 times 3, 5. The idea is still the same. We want to talk about what are the range of possibilities if we take one number in this interval and another number in this interval and we multiply them. What is the range of possible values that we can get? And that's the same as asking what's the smallest possible value we can get and what's the greatest possible value we can get. Well, in this situation, the smallest possible value is going to be a negative number when you multiply this minus 1 by, not by 3, but actually by 5. Because that will give you minus 5, which is smaller than minus 3. And the biggest possible value out of these four is 2 times 5. So in this case, the endpoints are minus 1 times 5 and 2 times 5. The 3 is being completely ignored. Here's another example, minus 4 minus 3 times 1, 2. What's the smallest possible value you can get? The smallest possible value is minus 4 times 2, while the biggest possible value is Well, it's going to be a negative number because this is always negative and this is always positive. So it's always going to be a negative number. So we're looking for the biggest negative number, and that's going to be minus 3 times 1, or minus 3. So in this case, it's minus 4 times 2 as one endpoint, and minus 3 times 1 as the other endpoint. I'll let you check the other cases. With minus 5, 1 times minus 2, 3, the smallest value is minus 5, 3. And the largest value happens to be minus 5 times minus 2. Here, the smallest value is 2 times minus 6. The largest value is minus 1 times minus 6. Here, the smallest value is 0 times, well, any one of these, so 0. And the largest value is minus 7 times minus 1. And here, we have a minus 2 times minus 1, that's a 2. And largest value, minus 3 times minus 4 is 12. And now let's check the associative law, see if that's going to hold. Because this is a rather complicated type of multiplication, so it's much less obvious now that associativity is going to hold. Commutativity is pretty clear because it's sort of symmetrical. These four numbers that we get don't change if you swap those intervals. But associativity, let's have a look. Here's an example, minus 3, 1 times minus 2, 4 times minus 5, minus 1. The product here is, so the smallest possible value is minus 12, the biggest possible value is 6. That times this, and then looking at these two, the smallest possible value would be 6 times minus 5, that's minus 30. The biggest possible value would be minus 12 times minus 5, or 60. The other way around, with this product in brackets, so this product is smallest possible value would be minus 20, biggest possible value would be plus 10. So that times minus 3, 1, and then the smallest possible value is minus 30, and the biggest possible value is 60. It looks like associativity works. So what do the laws of arithmetic look like for this interval arithmetic with integers? Well, there's the commutative laws. They're the same as with natural numbers. And we have associative laws. It turns out that both associative laws work even in this interval over integers situation. And this one here is the one that requires some discussion, because this one here is kind of obvious. But the associative law for multiplication, how can we see that? Suppose the intervals happen to be A, B, C, D, and E, F. Then what you should think about is you should think of all the 8 numbers that you can get by multiplying one of these endpoints with one of these endpoints with one of these endpoints. So A times C times E, or A times C times F, A times D times E, or A times D times F, or B times C times E, or B times C times F, or B times D times E, or B times D times F. The endpoints of both of these intervals are going to belong to these lists. And both of these lists belong to both of these products. For example, say BDE. Why does that belong to here? Well, because BD is one of the possible products of I times J. And so since it's one of the possible products of I times J, when we multiply it by E, we get one of the possible products BD times E in I times J times K. And why is the same BDE appearing in here? Well, because DE is one of the possible products when we multiply J times K. And so B times D times E is going to be one of the possible products when we take this times the product of these two. So it's by looking at these various 8 possible endpoints and seeing that they're in both of these things that we can see that the two different associative products agree. Although it is definitely a little bit more subtle than it is in the natural number situation. And what about the distributive law? So the usual distributive law does not hold for integer intervals. But a slightly weaker version of it, the sub-distributive law, does hold. And here's what it is, that if you have 3 intervals I, J, and K, and you multiply I times j plus k, that's contained in I cross j plus I times k. And by that we mean that any number which belongs to this thing belongs to this thing. Let's illustrate it with an example. Minus 2, 1 times minus 5, minus 1 plus minus 1, 3. The sum of these two is minus 6, 2. And then when we look at the product here, the smallest possible value we can get is 1 times minus 6. The largest possible value is minus 2 times minus 6, or 12. The right-hand side, minus 2 times minus 5 minus 1, plus minus 2, 1 times minus 1, 3. What's that? This product is minus 5, 10, because the smallest value is minus 5, the largest value is 10. This product is minus 6, 3, because the smallest value is minus 6, and the largest value is 3. And when we add these, we get minus 11, 13. And so we do indeed see that this interval is contained in this interval. And as before, we can remark that these two particular intervals play an important special role. They're playing the role of the numbers 0 and 1. 0, 0 plus any interval is the same interval. 0, 0 times any interval is 0, 0. And 1, 1 times any interval is the interval. In fact, the integers themselves are sort of sitting inside this interval arithmetic, just as those intervals of the form n, n. So we're getting an extension of the arithmetic of the integers to the sort of larger, somewhat more ambiguous intervals. When we move from integer intervals to rational number intervals, much of the story doesn't change. So the various laws having to do with addition, multiplication, subtraction are exactly the same as they are for the integer intervals. The difference, however, is that now the possibility of division enters the picture, because that's the operation we can do with rational numbers that we couldn't do with integers. So without going through all the details formally, I think you can get the idea. The rational intervals, or intervals with rational coefficients, are expressions that look like this. Square brackets, rational number, comma, rational number, where this rational number is less than or equal to this rational number. Addition is defined just as before. It's this plus this, comma, this plus this. Multiplication is defined in the same way as it was for integer intervals. We have to look to see which of the four products is the smallest and which of the four products is the biggest. So with these examples, the smallest value would be when we take this minus sign here and multiply it by 3/4. So minus 3/4 times minus 1/3 would be minus 1/4. And the largest possible value we get when we multiply 3/4 with 1/4, giving us 3/16. Now what about division? Can we divide this interval by this one? Well, that would mean that we take some arbitrary rational number in here, some arbitrary rational number in here, and perform the division and see what are the range of possible values. Well, unfortunately, that's a little bit problematic here, because in this interval is the number 0. So one of the numbers in here is 0. And we're not very happy about dividing by 0. So we're going to exclude this as a possibility. We'll say that we are not allowed to divide by an interval which contains 0 in it. However, the other way around would work. Here's an interval containing 0, but this interval doesn't contain 0, so we can divide this by this. And what should that mean? Well, again, it's the same idea. We look to see what are the range of possible values if you take some number in here and divide it by some number in here. What's the biggest possible value you could get? What's the smallest possible value you could get? Well, let's start with the smallest possible value. The smallest possible value, let's see. If we divide this by this, it's really the same as multiplying by the reciprocal. So that would be minus 2/3. If we divided this by this, well, then we get the reciprocal, so it would be 4/9. Minus 4/9. That's bigger than minus 2/3. This divided by this, or this divided by this, would be positive, so that's not going to help us. Minus 2/3 is the smallest possible value. And the biggest possible value, well, when we divide this by the smaller of these two, we're going to get 1/4 divided by 1/2. That's the same as 1/4 times 2, or 1/2. That's bigger than if we had divided it by this, in which case we would have gotten 1/3. So there is an introduction to interval arithmetic, which has been discovered and rediscovered probably many times in the course of mathematics. And there are some articles and perhaps even books that are written on this subject. It's useful for us for a number of reasons. First of all, it gives us the orientation that scientific work is important. Even if you're a pure mathematician, it's good to orient ourselves towards scientific work, towards empirical observations. And if we have a mathematics that corresponds well to what a scientist is doing out there in the real world, hey, that's a good thing. It also emphasizes for us the importance of intervals. The idea that we can capture uncertainty in a precise kind of way by working with intervals. In some sense, analysis is all about intervals. It's about errors, uncertainty, and trying to control them. We'll talk more about that, and we'll see the importance of intervals as we proceed further on. I want to finish today's lecture by having a look at those two questions that I gave you last time, having to do with a simple computation over the rational numbers and another simple computation, supposedly, over the real numbers. So last time I asked you two questions, one over the rational numbers and one over the so-called real numbers. Let's have a look at those two questions. The first one was to calculate or find the sum 1/2 plus 1/3 plus 1/4. And I asked you to write the answer down and circle it. Let's do that. Okay, so to calculate this, I need to know something, and I need to do something. I need to know that I need to get this over a common denominator, and I'll use the least common multiple of 2, 3, and 4, which is 12. So in my mind, I'll convert these to fractions with a 12 in the denominator. 6 over 12, 4 over 12, and 3 over 12. And then I'll add the numerators, 6, 4, and 3 to get 13. So the answer will be 13 over 12. And we'll circle it. And we'll feel happy because we've actually done something. We've actually made a calculation. We've gotten an answer that can be checked. That was the first question. The second question I asked you was over the real numbers. Now, you probably know by now that I don't believe in the real numbers. I think that modern mathematics is seriously astray in its denial of the problems with real numbers and the very sloppy logic that has pervaded a lot of mathematics coming from thinking unclearly about real numbers. It's a very sad situation, in fact, and many mathematicians and students have been almost programmed to think incorrectly about these things and to not look in that direction to even see that they have logical problems. So I want to weaken this idea. I'm not going to be able to do this so quickly, so I'm going to have to kind of slowly shake these false ideas from you, planting seeds in your minds. So this is one of these attempts. I asked you to calculate, to find the sum of arguably the three simplest irrational numbers, which are square root of 2, pi, and e. So, what do you have to do in order to calculate that sum? It's a calculation. I wonder how many of you wrote down an answer and circled it. If you did, my guess is this is what you would have done. This is the standard response. There is no better way of expressing this that is at least known to mankind. And so one is forced to simply repeat the question to get the answer. It's a vacuous, kind of empty arithmetic that doesn't leave us with a very good feeling. We feel as if somehow we're cheating and we don't really know what's going on. Both feelings are more or less correct. All right, I'm going to be saying a lot more about real numbers later, but I just want to plant the seeds that all is not well in the happy land of modern analysis. Roughly speaking, the thing doesn't work. Okay, eventually we're going to be talking a lot about real numbers. I'm going to lay it all out on the table. We're going to look at it in great detail. We're going to roll up our sleeves. Nothing is going to be left under the carpet. Okay, so we're slowly moving towards that, but I want to establish some positive things first, so that when we move modern analysis to the side, there will be something else that we can have in its place. Okay, so next time we're going to look at Isaac Newton's famous algorithm for finding the zeros of a function. We're going to apply Newton's method to talking about polynumbers and then to algebraic curves. Very important algorithm, very interesting stuff. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.